Great. Right, okay, what we've got here then is we're going to look at something called Dijkstra's algorithm, which no one can spell, no one can pronounce, but I've spelled it like that, I think it's right. Dijkstra, something like that. Quite an important computer scientist, mathematician. Okay. What the algorithm does is attempt to find the optimal route between a start and end location. Now, what we generally define these as are nodes. Okay, this is what we call an undirected graph. We have got nodes which I've just labelled with letters. Okay, and then we have routes between the nodes. Okay, and these are two-way. In fact, yes.
Between N and N.
Yeah. This one, 2, 3, 3. 2, 3, 3. Okay, so the way that the algorithm works is we look at costs. Okay, and the way that Dijkstra works, it starts off from the start node and says, how much is it going to cost me to get to my neighbours? Okay, and the cost to get from a node to its neighbour is the distance. Now, this isn't just like meaning for physical distance. You can represent lots of different things. You could have resistance of a wire. Could be these values. It depends what you're doing. You can use this for more than just looking round how to get from one location to another on a map. Okay, you can use all this when you're doing networks and transmitting things across networks. So these distances could be traffic load on a particular route through a network. Okay, but we're just looking at this, and the key thing to look at, and this is from one of the questions on the practice paper, these distances bear no relationship to the physical distance between the nodes. Okay, so you never ever worry about where they're actually positioned. You look clearly at the numbers. Okay, right. The first thing that gets set up once you've identified your start and end nodes is you build this little table where you write all the nodes down and you put, for all the nodes that set the start location, a cost of infinity. Okay, which we normally, obviously, I'm assuming everyone knows what the infinity symbol looks like. Okay, the symbol that we use, Mobius strips, is where it comes from. Another brilliant German mathematician. Right. So we start off like that, and the process is pretty magical. It isn't very complicated. All we do is we've got a loop running, and every time we start the loop we say find the item in this list. This is what we call the open set. Find the thing with the lowest cost. That's what we do. That's how we start the loop each time. So if we look at that, which node has got the lowest cost so far?
H.
Everyone happy with that? H is the start node. It's obviously going to have a cost of 0 because to get from the start node to the start node costs nothing. Alright, so that's how we can just say, oh, it's 0. Right, so what we then do is we say, okay, who are the neighbours? Now we can see from the diagram that G and N are neighbours of the H node. So we look at the neighbours and we say, okay, how much is it going to cost us to get to those two neighbours? Alright, so I'll just move the algorithm on. Right, so the blue ones that are highlighted, yellow just means the current node we're investigating. So we've highlighted the G node. To calculate the cost to get to G, we look at the node we're on and we look at its cost. So if we look at H, cost nothing. So we've got that cost, so it's 0 plus something. The distance to get to G is what we add on. So we go 0 plus 25. So to get to G, it's going to cost us 25. Now what this algorithm does is it keeps track of the overall cost to a particular node, so we can always work out the distance that we'll have travelled, okay, in total. So we mark that down and we put the parent down. Okay, so it's alright, that was travelling from H. That's important so that we can work the route back when we get to the end. Let's have a look at N. So N is 210 from H. So the cost to get to H was 0. So the cost to get to N from H is 210. Now actually there's something else that's happened here. What we do is when we actually work this little costing out, if it's better than the current cost, we update. Okay, so that originally was infinite and there was no parent. So we say, oh, 210 is smaller than infinite. That's why we set them all to infinity. So we better update that and say that we came from H. So a situation that you get, not necessarily in this graph, but I'll show you another graph where we do update. The situation you might get is that you say, oh, actually, I can get to a node further on quicker from a different route. So we need to do updates so that we keep the optimal route alive. Okay? That's the end of the loop. That's it. That's Dijkstra. We just keep going now until we find the node or we find there's a break in the graph. But we'll come back to that. Right, so we've done one loop. What we do when we examine a node, we put it as visited. So that now goes into what we call closed set. So we don't look at that one again. That's important, otherwise you get stuck in the endless loop. You don't want to do that. Right, so we're going to start the loop again, and we're going to look for the one with the lowest cost. Which one is it going to pick? G. Yeah, is everyone happy with that? G's very much lower, but we just pick that one. So when we iterate this time, we pick G, and we look for its neighbours. H is a neighbour of G. Everyone see that? But I haven't bothered picking it. And the reason I haven't picked it is because it's in the closed set. Okay, we're only interested in nodes that we haven't physically been to.
What was the closed set again?
Pardon?
What was the closed set again?
Closed set is just a list of all the nodes that we've visited. We've physically been and examined. So we started at 8, so it immediately went into the closed set. So you can see G, and I marked these in black. So G, because it's the one I'm visiting, we start in and put in the closed set. So we won't take part in any more investigations. Right, so I identified L and M. So what I've done is I've gone, okay, how much is it going to cost me to get to L from G? So I'll look up the cost of G, which is 25, and I say, right, 51 is the distance, whatever that means, between G and L. So add those two together. So I get 76. And I put down that my parent, where I came from, was G. It's the literal interpretation of the word parent. I do the same for M. So I say, and one thing to note, this was from an exam paper. Look at the numbers. They're horrendous. No calculator. No calculator. So be dead careful with these numbers. Right, so I'm going to calculate the cost between G and M. Don't look at the diagram, look at your table. Don't make the mistake of trying to work it out on the diagram. It might get more complicated than that. That's trivial, that is. So I'll look at the cost to get to G. I've got to add 25 to 176. Luckily the computer's worked this out for me, but I probably could have carefully got to 201. And I put that in and I say that was from G. That's all the neighbours' costs calculated. Do the loop again. So which one's going to get picked this time? Yeah, everyone happy? It's L. So we look at L. We look at its neighbours. G was in the closed set, so we ignore that. But we look at E. Right, some hideous numbers now. So we say, how much does it cost us to get to E? So we look at how much it cost us to get to L, which was 76. Notice L's in the closed set, so it's not going to be involved in any more searching. So 76, the distance, 307. Hideous number to add together. Is it not? So 307 plus 76 gives us 383. Okay. There aren't any other things to update. So that's the end of that loop. So we do another loop. Which one's going to get picked this time? Which? Everyone happy with N? Yeah? Right. So we run round again. And we say, okay then, our neighbours are N and E. We pick E again because it's still in the open set. The ones that are white haven't been physically visited yet. They're just looked at as neighbours. Right, so we've got a calculation to do. How much does it cost us to get to E? So we look up how much does it cost us to get to M. So that's there in the costing, 201. So I've got to add 201 to 185. Okay, that is 386. Everyone happy with that? Right. What we must do is look at the cost that's already there. 386 isn't better than that one, so we leave it. Okay, if it had been better, we would say, oh, update the parent to M and put the cost in. Yeah? So we don't. We say, okay, that's fine. Now, the other one we've got to examine is N. So we go, okay, the cost to get to N from M. Now, hopefully you can see this in the diagram. This is like a non-starter. So it's 201 plus 233. 400 and something. Much bigger than 210. So again, we don't update. This is why this isn't a very good example. We'll show you as an exam question. Okay, right. We've got two items in the closed set. Which one's going to get visited next time? In the open set. Which one's going to get visited? Yeah, N. Even though it's a dead end and we know it's not going to provide a solution. Oh, I've added a node there. Hang on. Right. So I'll visit N. Goes into the closed set, so it won't be any part. It hasn't got any neighbours that aren't in the closed set. H is in the closed set. M's in the closed set. So we actually don't do anything. So that was like quite quick. Right, we've got one item left in the open set. What's going to get picked? E. This is where we're trying to get to. So if we run again, we pick E. If we arrive at the node we're looking for, we stop. Okay? At that point, we can work out the path. And we can do that by following the parents. Alright, so E's the one we want. We can see the parent is L. So we write that down. We say L. If we look at L, we look at its parent, G. We say, okay, we got to L from G. Remember, this is kept track of what was the cheapest route between these nodes. So we go, okay, G. We then look at G. And we say, okay, who's the parent? Oh, I came from H. So we go, H. Then we look at H. We don't assume it's the start node. We just look at H and we go, oh, there is nothing. What term do we normally give to something where we're not pointing to anything?
Space. 0.
Let's do Hangman, live on video. No vowels. I'll help you by showing that's a vowel. A pointer to nothing.
No.
Null. So you get it. You're ruining my Hangman game again. Null. So we stop when we're working back through this. We keep going back to nodes and say, who's your parent? If we find a null, we say, oh, that must have been the start then. And you can see that is the root. And that's exactly what the computer's doing in this little program I wrote. And I've then done a lot of fancy stuff and highlighted it in red. Okay, anyone got any questions about that? It's pretty much straightforward. I've got a better version of this program. I don't know why it hasn't loaded up. I'll have to load it up in a sec. Okay, right, I'll stop the video there and we'll do another one with a more complicated graph. Okay, and I'll load up the other program as well.